So our next presentation is from Francesco Trevisan. He is a senior additive manufacturing expert at Wärtsilä. He's going to be looking at the adoption of laser powder bed fusion for marine engine components, specifically a case study that he will be highlighting for a redesigned 3D printed cylinder head with optimized cooling, reduced weight, integrated subsystems. So a case study that really highlights the potential for innovation using additive manufacturing. So as you're ready, over to you.
Oh, good.
Thank you.
Thanks. So good morning, everybody. Today we're going to go through basically what is an application of additive manufacturing into industry. Wärtsilä is in the marine market, and we are basically a very huge company, particularly in what is concerning the production of these kind of products. These are large-scale engines for marine power plant. And basically, as you can see, our engines can be in different modules, different configuration. And we are mostly working with the combustion technology. Combustion technology, which means that, of course, in the past years, we have been using quite a lot of diesel, carbon fuels. But time after time, we also passed towards the more ecological and, for example, fuels coming from biosources, or to now the green fuels, methanol, ammonia, and in the next future, also hydrogen. So this is basically the impact that we can consider over the world for Wärtsilä products. So 1/3 of the world vessels is equipped with one of our auxiliary engine, or over 180 countries might have one of our applications installed. This is an impact where you can see how, for example, reducing CO2 on the product performance might have a huge impact, or reducing the cost might have a huge impact on the market, on the products. But then, where is IM? We started as a small team, and basically now we have been establishing more the utilization of additive manufacturing technology that luckily you have seen in the previously presentation. And we adopt additive manufacturing in 3 main areas now. First of all, manufacturing assembly, how to make the assembly of our engine smoother, faster, cheaper. Spare parts and service operation, everything that is done after the selling of the engine, can be also implemented with additive manufacturing technology. Lighter tools, faster, cheaper tools. And research engineering means all the development of new products new parts that can go on the products. So this triangle of performance allows us to have an impact on the technology. We don't say that additive is revolutionizing the concept of the engine, but it's giving a boost to the innovation, and it's giving also the boost to what is the basic implementation of that. For example, this was our previous roadmap. So we started as a small group, and we started with the quick wins, the tools, the fixtures. We start learning, we start establishing the workflow, the know-how on how to use 3D printing. We use a lot of plastics at the beginning. Then we started also to learn how to use the metals, how to replace parts, how to make additive manufacturing really advantageous for our company. Until we even reached the first serialized part mounted on the engine as 3D printed part. And from then it was reaching the plateau of performance part, the integrated systems. So we already reached the terms in Wärtsilä as team, as knowledge, as company, as R&D, where basically we can integrate the best benefits of additive manufacturing, both metal and plastics. This is an example where, for example, 88% of weight reduction lead also to 20% cost reduction, even more at the beginning. And this is, for example, a really apples-to-apples comparison. In this way, we were fixed to keep the same geometries. But this was the first approach. Because then we have also new thinking, new approaches, new challenges. This is, for example, a heat exchanger that we have been studying basically in the rethinking how can we adopt additive manufacturing in the heat management. So this is still on the prototype phase, this is still on testing, but already for us was the biggest sprint we ever done, was already for us a long journey because we studied in 2019, studying the lattice properties, the heat exchanger properties of lattice, and also the printing phase of such 40 kilos of stainless steel was not easy, and the collaboration through the partners, the supplier, helped us quite a lot to basically understand the limits and also challenge a little bit the limits of the technology itself. So in this case, for example, is a water-to-heat heat exchanger, and I'm highlighting this because it was really a nice result to obtain. This is printed and basically also tested now in this month. It will be tested. And this also opens up the idea that, okay, but if we can integrate a part, why we don't rethink also a system? Why we don't rethink many components put it together? This can be a series of heat exchanger. It can be integrated in a more complex part. And this takes me to another market. This, I wanted to thank you, my colleague Sai, who gave me this idea for this presentation. So this is a supercar. I'm not expert in Formula One or in supercars, but this is high technology product car that can be not by engineers, maybe really rich engineers. But the funny story about this is that for example, this profile was coming from the Formula One car. So this is the sport car, where the top of the technology, the engineer was applied, the top of the skills and also the cost, the innovation was applied. But then exactly they took this detail and they applied it in the product car. So I took this as an example that by boosting the innovation in a certain product that maybe is not a product, it will be never commercialized, you can take a simple detail and export in the real product to improve the performance. This is how in Formula One and other sectors is working. And I wanted to use this metaphor as a bridge for this cylinder head. So we started last year a project to redesign, rethink what is one of the most critical components in our engine, the cylinder head. This cylinder head is for a medium bore engine. You can consider that it occupies a volume of 500 per 500, almost, a little bit, not exactly a cube, but basically the idea was, can we show to our colleagues how will be the innovation in these critical components? Can we basically use the additive manufacturing to enable the design freedom in this component and, for example, combine multiple parts, multiple systems in the same one? And this is where we started. We started with the design, we started with the simulation. Now we're going to be entering the manufacturing phase next year and testing phase also next year. Because we want a technological demonstrator to open the mind to our R&D engineers, showing that maybe this won't be a product, maybe, but maybe we can learn more on how could be the cooling, how could be, for example, the iteration of a better heat management. This might sound crazy, might sound quite futuristic, but again, we want to show what could be the performance outcome, because maybe we can take a single detail and take it out. For example, what is nice about the iteration over the cooling system is that, for example, we were able to reduce the power loss. We were able to decrease the temperature rise in the water cooling system, which means that the temperature temperature exchange is working much better. And the thing is that this new concept of cylinder head is having less heat power. Why less cooling power? Because basically we are localizing the cooling power where we need. So we need less power to cool, because before we were cooling basically homogeneously or all the structure that was not needed. So now we can focus our efforts where really it's needed. Of course, we are talking about metal 3D printing. We try as much as possible to reduce the weight. It's not for the performance. It's not a cylinder head for motorbikes or auto vehicles. Here is more about we want to make it easier to print. We wanted to make it, what can I say, cheaper also to manufacturing, because the less mass, the less material, the less you pay. And here we have a different iteration, because we tried to push more or less the boundaries. And of course, we had also to simulate and to check. So basically, for each of these, we had to check, for example, the finite element analysis, fatigue analysis, and many different other simulations, validation. But this was wanting also to highlight how we use topological optimization. We use topology to do this because we were able basically to iterate the same workflow, and it was much easier to change the CAD or, for example, positive and negative bodies inside the workflow, enabling a faster iteration. And here exactly what I was mentioning. So this is something we already discovered many years ago, that having a nice concept design, particularly with the topological optimization, lattice integration, and many other computational design, you need a tool that you can iterate fast, because otherwise you are spending a lot of time in changing each single simulation. And this was helping us to save tens of hours, and this means money, and this means also project successful. What else to say? Here in the picture you can see, for example, I put two images of the topological optimized body. Of course, still we need to pass to the CAD for the machine phase. Still we have to pass to some additional, let's say, traditional CAD features. But I think that in the future there's going to be more innovation helping us to go directly also with this computational design. Last but not least, basically I wanted to highlight another thing that was related to this. When we talk about additive manufacturing, we always focus about the final weight of the part, or we focus on how much material we're using, how much laser time, material time, and so. So basically, how is the process and how is the feedstock? But many times in our history of additive manufacturing introduction in Wärtsilä, we face the problem of the file. File dimension, it's really tricky when we go to very complex structure, like this one, like the heat exchanger I was showing before. And this is also what we are really interested in the file management. Because if we are talking about a very complex part like the upper one, or like this one, which is more a demo piece that you can find at least free around Formnext, the idea is that the file dimension can be quite tricky, and this implicit interop will be something that we look forward in the application in the industry, not only for laser powder bed fusion, but also for other technologies. So, the next years, I would say, there's going to be the manufacturing phase, the machining phase, and the testing phase. This project for us will be quite critical, meaning that with such big, large-scale machine, we cannot fail. We don't have the luxury to fail so much. So we have to consider a lot of safety factors, both in the design features or in the design simulation, safety factor in the machinability, because Inconel is not easy to machine. So we had to add at this time a lot of machining allowances, as well also in the testing phase. So for us, it's going to be a challenge, but challenge means also opportunities. And this is a picture of one of our middle bore engine, 20-cylinder configuration, I think. And we're going to test on a single-cylinder engine, because that's also one thing that many times in additive manufacturing industry we don't perceive is the time to develop, the time to bring a validation. Because for us in Wärtsilä, to have additive manufacturing material used in critical components, it took 5 years. To have this cylinder head tested, it will take, first of all, a small amount of hours on a single cylinder engine, then possibly more hours. And then if we wanted to take further on, we're going to have multi-cylinder engines, so it will take years. But that's, unfortunately, or it's the status of the art in terms of validation. And we are not even the longest one in the market. If we think to aerospace or aircraft is even longer. And now I'm an Italian living in Finland. I think this is really nice, and I wanted to conclude it also with this picture because northern lights are amazing, and it's also showing that it's nice to follow the additive also in places that I didn't think before. But what I wanted to conclude is that it's not only about the technology. It's not only about the know-how. It's a lot about the culture and the strategic thinking. Because you can have the best machine on the market that allows you to print large-scale parts. Or you can have a lot of experience in design additive simulation, additive manufacturing. But if you don't have this third element inside the company, inside the organization, so be open to test, be open to try, be open to evaluate new possibilities, this gear system doesn't work. Because you might have the large printer, but you don't have the culture that allows you to test it. Or you might, for example, having a lot of knowledge, but you don't have the freedom to apply it. So I wanted also to mention this, because this is, I think, one of the core messages of this cylinder head. It's not about the product, it's not about the money at the end, it's about learning, it's about improving the innovation inside the company, and innovation can lead to unexpected results that are not, let's say, highlighted when the project is started. Those are hidden, and those are usually the one that brings the more benefits, because it might be beneficial for maybe colleagues that are not even working on this system, but they are working on other concepts. And I was a little bit more faster than expected, but if you have any question, please, you can ask me now or later on. Thank you.
Thank you, Francesco. Any questions from the floor? Or you can catch him after and ask him. I just wanted to ask, on that last piece, you're talking about the culture. Obviously, that is, in many ways, it's more difficult to implement that than it is a new technology. So what are some of the strategies that you've used at Wärtsilä to encourage that culture of sharing and connect the knowledge and the technology? How can people achieve that themselves?
Thank you very much for the very interesting question. This is a hard topic for us. We discussed many times. So we are a conservative company with conservative R&D, which is a good thing, which means quality, which means very robust product. And this means that our work in introducing a new technology has been very hard. And my colleagues, my managers here can confirm that. It has been a work of ensuring the trust in the people, that they can trust that additive manufacturing can work. So we had to take all the baby steps and take the engineers and experts by hand to show that additive manufacturing works. Because at the end, in our research and development department, facta means more than words. So it has been more on taking, as I showed in the roadmap, small little example or even bigger example, but taking the data to them and showing that it works. And when it works, you raise the bar a little bit, and you raise the bar a little bit. And the other thing was keep on going. Never leave never think that the wall is stopping you. You just have to find another solution to pass the wall, or another solution to climb the wall, or to break the wall. So I think that to move this cultural change in the organization, my approach personally is a bottom-up approach. Start from simple, prove that simple works, and raise the bar each time. But as well in the team, we have the nice thing to have multiple point of view, so also the top-down works. When you go with these projects, these are really open-minded for the engineers. Mm-hmm. So I think that a balance between the two is working much, much more performantly. So.
Perfect, thank you. So keep an open mind and bring your team here to the application stage where they can see for 4 days that additive manufacturing does work across all these different industries. Francesco, thank you very much.
Thank you. Thank you.